Malyuzhinets and Wiener Hopf technique, and as I understand it, this lecture will be shared, right?
Yes.
So you should do roughly the first half.
Yes.
So when do you want me to tell you?
Stop! I'm in the middle. In the middle.
In the middle.
In the middle. Okay. 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 Try to stop me. Okay. So the topic of this lecture from me and Professor Bernard is the wedge problems. It's a classical scattering problems, and there are many solutions available in literature for this kind of problems from Sommerfeld Malyuzhinets technique, and we have extended generalized Wiener Hopf equation to generalized form, and we show in literature several results in closed forms and using the freedom factorization exposed in the first lectures yesterday. Okay, so here I will present first closed form solutions and formulation in terms of generalized Wiener Hopf equations, and then I will show how to implement freedom factorization of the first lectures in this kind of problems. The summary is reported here. So we'll show generalized Wiener Hopf equation for angular region problems. The classical example is a wedge problem, and we show some exact solution to be compared with the Sommerfeld Malyuzhinets technique, starting from the easiest one, the perfect electric conducting wedge. Sorry, I'm talking always about electromagnetics, so I know that there are different subjects here, and electromagnetics is not the most widespread, probably, acoustic, fracture mechanics, and so on. And then we apply the freedom factorization to generalized Wiener Hopf equation, and we will show some approximation or approximate solution. Here is some literature about this topic, or in addition to the one presented in the first lecture. There is the main basis of the method is reported in this paper of 2003. Then we have some properties and alternative method reported here. The properties will be used to get diffractions and the Sommerfeld functions, and that are useful also to compare the Wiener Hopf solution to the one obtained with the Sommerfeld Malyuzhinets technique. And then here there is another paper about the method that we have presented in Days of Diffractions in 2005. I recommend this conference. It's very interesting from a mathematical point of view. There were sessions about Wiener Hopf in scattering and diffractions. And here is one of the main reference with results about impenetrable wedge at skew incidence when you have anisotropic surfaces impedance, so the general problem about wedge. So let's recall what are generalized Wiener Hopf equations. The equations have unknowns, the plus unknowns and the minus unknowns, that are defined into different complex planes, and these different complex planes are connected together with a mapping. And I repeat here, the framework will be electromagnetic, so sorry for the quantities that I report in these presentations. Here, to get familiarized with the notation that I use, I found this table of analogy between acoustics problem and electromagnetic problem, TMZ or EZ polarization. You see the quantity, the electric field components, related to the magnetic field components. Here I reported the electric, magnetic, permeability of materials, and here I reported the quantity that are related to the acoustic, equivalent acoustic problems. So I reported this notation to be more familiar with this. And in particular, we consider the perfect electric conducting a condition, the soft boundary condition about the Dirichlet in EZ polarization. So let's start from the generalized Wiener Hopf equation for the angular region problem. This is an angular region defined by phi equals 0, phi equals gamma or gamma 1. I will gamma will be gamma 1 in these first slides, then I will add the second region, so I will have also a gamma 2. And these are shapes of the problems with wedges, and we have a z dependence that is of this form, exponential of minus j alpha 0 z, and we have beta is the zenithal azimuthal angle for skew incidence, phi 0 is the azimuthal angle of incidence for a plane wave, and here we have the propagation constants in terms of material parameters, and alpha 0 and tau 0 as the propagation constant along z and rho. And here we define the unknowns, the transformations, the Laplace transformation of unilateral Fourier transform of field components in a radial direction. So for each phi we define the transformation with respect to the radial direction of the Ez, E rho, Hz, H rho component. So we see a propagation along phi, and the transverse component are the one reported here, and we call this V and I. There is a connection like electric field, potential, magnetic field, current, and so on. We will use this notation. Starting from the Helmholtz equation reported here, we will use different coordinate systems. In particular, we will use oblique Cartesian coordinate systems that is reported here, u, the variable u, and v along the face, phi equal gamma, gamma 1, and here is the connection between the Cartesian coordinate x and y and the u and v, and we report the Helmholtz equation into these new systems, and we get this Helmholtz equation in u and v. Then we apply Laplace transforms to this equation, and we get this equation in eta, where we have applied the Laplace transform. And these terms is the initial condition of Laplace transform that is reported here. So we have a second derivative, so the term is a little bit complex, but it's this one. And to get the solution of these equations, we use characteristic Green's function procedure, classical procedure. We took inspiration by Felsen-Markovits' book, and here we have the solution in terms of an homogeneous solution and a particular solution in terms of the Green function. The one in the box is the Green function, and this is the forcing term. And here we have the homogeneous solution. To get the exponential of the homogeneous solution, we solve the characteristic polynomial here in terms of m, and we found these two solutions. We get for this term the one with the arrow on the right. It means that this is convergent to the infinity, and this is the other solution. To get the Green functions, we use the procedure of Felsen-Markovits' book. And so to show the terms here, there are dependence on the aperture angle gamma, and then we have dependence on the Laplace variable eta and xi. Xi is this term, the spectral propagation. And we assume that the proper sheet is for xi 0 equal tau 0, for eta equals 0. Now, let's specify this form of solution for v equals 0. So v goes to 0. In this case, for v equals 0, the Laplace transform of the E field becomes what we have defined in advance in terms of radial Laplace transform. It's the v plus eta for phi equals 0. So we get this, where m is this. And by applying the Maxwell equation and using the Laplace transform, and we represent the Laplace transform of hx, that is equal to rho. In this case, for v equals 0, x and rho are the same coordinate, and we get a representation of I rho plus for in terms of the Laplace variable eta and phi equals 0. This is the expression. Now, we have these two expressions. We can eliminate the arbitrary spectral constant here by elimination of A and by specifying what's the Laplace transform of f eta. F eta was the initial conditions on Laplace transform. We get this representation. We use a representation of the field components using Maxwell equations, and by substitution we eliminate A. Thus, combining all of these equations, we get this. So let's comment this equation. You see there are combination of Laplace transforms of E and H field along Z and rho component for when you see phi equals 0. So the component here are related to the components reported here. The components here are the Laplace transforms of the field along this direction for phi equal gamma 1. You see, this is an equation, a functional equation, where you have unknowns that are defined in eta and unknowns that are defined in m, and the m is connected to eta through this relation that we have seen before, solving using the characteristic Green function procedure. So, if we repeat the same formulation for the wave equation in terms of hz, we get a similar equation. So you look, they are similar equations, so with spectral components of fields of along phi equals 0 connected to the spectral components along phi equal gamma. If we repeat the same procedure for a second angular regions, the one reported with the yellow arrow here, with aperture angle equal to gamma 2, we get similar equations. So you see they are of the same forms, and they are in terms of m2. m2 in this case is equal to m1, but we substitute the aperture angular gamma 1 with gamma 2. So they are very similar. Okay, let's go to a practical problem. The wedge, we take that the angular regions on top and the bottom are of the same size, phi, and in this case it means that the 2m are the m related to the upper region and the lower regions are the same. In this case, we apply surface impedance boundary conditions in a general way with anisotropic impedances, and we get from the equations shown before this system of equations. This is a matrix system. I will show what's G later. X plus is this, and x minus is this. So we have plus components in eta and minus components in m reported here. Okay, you don't see v rho plus here, v z plus evaluated in phi and minus phi because of the boundary condition. We have substituted and eliminated them. Okay, so we have this equation. This is a generalized Wiener Hopf equation because it's the plus unknown is defined in eta, the minus unknown is defined in m, and we have this component for the plus functions, for the minus functions. The kernel G is this, reported in this matrix form with S and D. The quantities here are the xi functions, the eta variable, alpha 0, and tau 0 are the propagation constant along directions, m defined here, and n is this function. So we have the equation for the general problems with impenetrable wedge at skew incidence, but to check the procedure and the similarity with Sommerfeld Malyuzhinets technique, first of all, I present a simple problem that is the perfect electric conducting wedge at skew incidence. To get the equation reported here, you go back to this system, imposing the soft boundary condition on the faces, or you can go back to this, imposing that the tangent component of the electric field is 0 on the faces, so you eliminate Vz plus here, and then V rho plus also. So you eliminate these components because they are 0 for the boundary condition, and you get this. This is a system that we can manipulate mathematically, and here are reported the manipulation, summing two equations, subtracting two equations. You get these systems of equations that is much easier to see. And we have plus unknown and minus unknown reported here. The one f and x are combination of the spectral unknown here. So we need to solve this kind of equation. This system of equation has a peculiarity. It's decoupled. So we have 4 scalar decoupled generalized Wiener Hopf equation. So we can proceed by factorization by equation after equation to get all the unknowns. First of all, we have to use some mathematical trick, that is to change the variable to another complex variable and transform the generalized Wiener Hopf equation to classical ones to apply standard procedure of factorization. And the mapping is reported here. Some studies has been done even by Raphael and about this kind of mapping, but the main properties of this mapping is these two properties, that plus functions in eta variable maintain their property. They are plus function in eta bar w, and minus functions in m variable maintain their properties in bar eta variable. It's not true the vice versa. So we have this property. So we transform these 4 independent equations, 4 decoupled equations into 4 classical equations. And here are reported some factorization that is useful to get the solution. You see here the equation depends on xi, eta, so we need to factorize eta and xi, and the factorization is reported here. To get this kind of factorization, you use logarithmic decomposition, and then you can also use the angular complex variable w to get this kind of factorization, or you can do directly in w by inspections, because we know an important properties that is not justified here, but the important properties is that plus functions are even function in w. Okay, here is reported how to get the solution. Since we are dealing with wedge scattering illuminated by plane wave, in this case we reduce the properties to an incident angle of phi 0 less than phi over 2. In this case we have that the plus unknown is non-standard in this case, and it's non-standard in the sense that you have a geometric optic component due to the incident wave that has a pull in the upper half plane. Here is reported the field, the spectral variable, the spectral unknown V in the spectral component or electric field, incident electric field in eta variable for a plane wave with incident angle of phi 0, and here the magnetic field, and these are the other two components at skew incidence. So we have said that we need to work on bar eta plane to have classical Wiener Hopf equations. So we transform these sources into bar eta using these relations, and then we have this. For example, we have equation A and equation C reported above that are rephrased in bar eta plane, and then we extract the source term through the geometric optic field, in this case the incident wave, and using this classical factorization solution we get finally this solution, that is Vz and Iz plus in eta plane, bar eta plane, for the direction phi equals 0. Okay. Similar relation can be done for the other two unknown, the V rho plus and the I rho plus, from equation B and D, that were reported here. B and D are expressed in terms of f and x, and f of x were combination of the spectral unknowns. Okay, the final solution is here, where we have also mapped the solution into the complex angular plane W, so to get closer to the notation of Sommerfeld Malyuzhinets method, okay, and using the reference paper number 2, we have from the Laplace transformation the relation to the Sommerfeld function for Ez and Hz, and these functions are defined in terms of the Laplace transforms components, as reported here. If we substitute these into these, we get this. Okay, so this is the classical solution for the perfect electric wedge at skew incidence. So we have this classical solution. So, okay, let's go to another problem, a classical problem of Malyuzhinets problem. In this case, we have scalar impedances. They are different from the top face and the bottom face, and the kernel is reported here. We can manipulate the kernel using this transformation matrix, and we get this. If you see this, the top portion on the left is the EZ polarization case, and the bottom right portion is the HZ components. So we have decoupled the two polarization in this case. So we have this kind of equation. In this case, we use the same mapping used before to transform the generalized Wiener Hopf equation to the classical Wiener Hopf equations in bar eta plane. Therefore, here is reported the EZ polarization only. So F is only these two components connected to these other two components, and G is reported here. Okay, in this case the kernel is much more difficult to treat, but we can rephrase this kernel into this kernel, where you see that there are constant matrices, then we have some already factorized terms here, and then we have a matrix to be factorized and a scalar to be factorized. Okay, so we need to factorize all the scalar and the matrix in particular. The matrix is of Danieli-Krapphoff form, so here I have reported the factorization, and the scalar can be factorized using this formula and this formula, okay, and here are other scalar terms that have been factorized and shown even before. Okay, so after that, after factorization, we have the closed form solution. Here is reported the closed form solution classically, and this is the residual of the incident wave, the sources, and to make a comparison with the solution given in Sommerfeld Malyuzhinets paper, when the solution is given in closed form, we have to rephrase some of the factorization terms reported here in using the Sommerfeld the Malyuzhinets function, the Malyuzhinets function, and after a big mathematical work, we have rephrased this term of factorization into this other, where we have the Malyuzhinets function, theta E and theta B are defined here, and they were connected to the surface impedance. ZA was defined here, probably, okay, here, okay, the classical way to define in terms of angle, okay, and T plus is reported here. If you substitute this kind of representation into our solution, then you get the same representation given in a Sommerfeld Malyuzhinets paper, and this is the Malyuzhinets function. Okay, let's switch to how many minutes I have?
You have 5 minutes, exactly.
5 minutes. So now I'm going to the approximate stuff. Almost repeat it quickly, using freedom factorization, solution for problems that don't have closed form solution. So in particular, a problem is when you have anisotropic and non-symmetric impedance phases, except in special cases. There are in literature. You have a set of conditions when you can get a closed form solution. This is particularly useful because when we apply freedom factorization, yes, you can take care of a closed form solution, but you have a procedure that can handle similar problems without taking care that you switch some parameter in your problems. So we have deduced the generalized Wiener Hopf equation spectrum domain. We will apply the freedom factorization. Then we will need some analytical continuation because we get approximation of the spectra in particular sheet or Riemann sheet. So in the proper sheet with respect to the xi variable, so we have to extend outside to get y, to get asymptotics in particular. And finally some physical engineering parameters. So it's more we think that this kind of solution is more flexible in general. Here is the equations reported before. I think I can switch this. It's a dense slide, but this is the equation to be handled, okay, with all the parameters for the case of anisotropic surface impedance. So first of all, we use the same mapping from generalized Wiener Hopf equation to classical Wiener Hopf equation, and then when you have a matrix Wiener Hopf equation, then you can apply the freedom factorization of lecture 1. So you transform this problem to this problem when you have a sources with a pole on the lower plane. When you have a source on the upper plane, you have this. Okay. We discretize this equation, but before discretizing, if you have weakly loss materials, it has shown in the lecture 1, it's better to warp the contour. So here is reported the location of the propagation constant. Then you can have branches here, you can draw branches. So the warping from the real axis to another axis, maybe this one, that connect jk and minus jk. This is another choice with respect to the rotation of pi over 4 reported in the lecture 1 as a useful one. We get more convergence because we are far away from the branch cut. Another important topic here is how we map eta and w plane. This is the mapping from eta to w plane. This is a mapping from bar eta and bar w plane. You can see this couple of variables, eta and bar eta, w and bar w, and has a parallel between the two. You can control the properties of a proper sheet in both planes, eta and w, bar eta and bar w. Okay, the relation between the w and bar w is reported here. Is simple, and this is the inverter mapping. This is the plane eta with the curve with the imaginary of xi equals 0, real key equals 0. Sometimes Mathematica that we use in our competition use this branch cut instead of this, or instead of vertical lines. So we have to check what Mathematica do usually. And here is reported the plane eta, and this is the plot of the same regions in a W plane. So you can recollect all the curve in this plane. Why we use W plane? Because we want to check the solution with respect to Sommerfeld Malyuzhinets, but also for another reason. It's easy to extend, to analytically extend the spectra when you use W. So we use that to rephrase our generalized Wiener Hopf equation problem in W plane, because in W plane you can get a difference equation, and from difference equation when you have solved your problem by discretization of freedom integral equation, then you get a sheet, a proper sheet usually of solution, and you want a solution also in the improper sheet to get asymptotics, and you use difference equation to go in the improper sheet, or to have the solution in the entire W plane that has replication of eta plane. Okay, so here is our equation. In this case, we have mapped between minus jk, jk, so we get this. Okay, it's this line is equal of integration in w bar w along the vertical line minus pi over 2, or if you are in w, phi over 2, minus phi over 2. So there is a sign here, and all the quantities here are remapped into these new variables. And we have this kernel M. M in this variable is very convergent and smooth, so that's why we use for angular region problems this kind of mapping, because it's very smooth, like you look, it's like Gaussian. And so we solve by discretization, simply by discretization. And here we have the analytical extension. After we got the solution in W plane, you can map back in eta plane, but before going back, it's better to work in W plane. If you work in W plane with generalized Wiener Hopf equation, you represent these in W, then using the properties that the plus functions are even function in W, you get this. This is a difference equation that connect the plus functions with the kernels. And you see that if you have a solution for a strip, for example from 0 to minus pi, then minus phi, okay, phi, to phi, because it's a even function, the plus function. So you can extend the solution to minus 3 phi, okay, and you get the improper sheet that stay here. So finally, we have to get the asymptotics of the field. To get this, we have to define the Sommerfeld functions using rotating waves, as done before, and we have the Sommerfeld contour, then we get asymptotics. And this is why we need to extend our solution, because the Sommerfeld functions capture values of the unknown that stay outside of the proper sheet. By asymptotics with SDP and UTD, we get a geometrical optics component, a GTD component, possible surface waves. Here is a check of the numerical solution in terms of GTD component, and the relative error is reported here for our numerical procedure. Here are reported some discretization parameter. You see that we have a logarithmic scale for the relative error. It's going down. When you have a 10 to minus 8, it's a very good quality solution for these parameters. Here is other test case. I have 3 test cases, then I stop. And test case coming from literature. This is a classical Sommerfeld Malyuzhinets problem when you have reported in the Senior Volakis book, and in this case you have a scalar impedance is isotropic, and you see the shape of the solution here. It's the same of the one obtained by us in these cases, and the solution is this one with this line, okay, in the middle. And here the results are reported in terms of geometrical optic component, UTD components after regularization of the GTD, and then you sum up the two and you get the total field that is continuous, like here. The physical parameters of the problems are reported here. Here is another solution in literature from Norris-Osipov paper of 1999, when you have an inductive surface impedance on the shadow region here, and in this case you see that for rough discretization you get very similar results. Here is the line is the one that have surface wave here, and as I told you yesterday, a freedom integral equation, when you rebuild the solution, the kernel is there with all the content of the spectral components. So the surface wave is a pole of your rebuilt solution. last, this is a kind of advertisement for this paper, is the penetrable wedge as a normal incidence in this case. In this case, the equations are reported here. We start from angular region 1. We repeat the procedure that we have done before for region 2, region 3, region 4. We impose continuity, so here are reported 2 regions, but we have to repeat for region 2 and region 4. Here are SIAM parameters. I don't go into details. In this case, we impose continuity on the phases of the dielectric. Then there is a not easy procedure reported in the paper, and we get the solution of the field with all the geometrical optic components, all the GTD components regularized through UTD. The solid line in gray is the total field for this kind of problems, and here is reported the comparison between the GTD obtained for the equivalent perfect electric conducting problems and the dielectric problems when you have a permittivity of equal 3. Okay, thank you.